Now, as far as isotopes are concerned, one thing that you need to know for this unit is that some isotopes are stable. And what I mean by stable is that, as an example, this is carbon-12. This is taken from the previous slide, and we know it's a carbon atom again because it has 6 protons. It's carbon-12 because it has 6 protons and 6 neutrons. This isotope of carbon, carbon-12, is stable. And what I mean by that is that if you had a carbon-12 atom, you could wait around probably for several million years, come back, and this carbon-12 atom would still be a carbon-12 atom. Nothing about it would have changed. It would still be carbon. Now, in contrast to that, okay, that's carbon-12. In contrast to that, there are some isotopes out there that are not stable. And carbon-14, as an example, turns out to be an isotope that is relatively unstable. What I mean by that is that if you wait around long enough, if you have a carbon-14 atom, and you wait around long enough, eventually this carbon-14 atom will change. It will turn into something else. So what does the carbon-14 turn into? Well, okay, here is our symbol for carbon-14. We've got the capital letter C, the 14 in the upper left, meaning this thing has a mass of 14, and the 6 in the lower left, meaning 6 protons. What does it turn into? I will show you with a very fancy animation. So focus your eyes on the atom here, and in particular right here. And what happens if you wait around long enough with carbon-14, one of the neutrons will turn into a proton and an electron. It turns out, if you remember from earlier in the course, the electrons don't really sit in the center of the atom, and because of that, this electron here that is made, if you wait around long enough, basically gets fired off into the distance. So there it goes, it just got fired off into the distance. And this atom here is no longer carbon-14. Well, the way that you write this as a chemical reaction is in this way. You say you start out with carbon-14, and it's on the left side of this arrow. And then carbon-14, if you wait around long enough, turns into something else, and that something else is a question mark right now, and it also fires off an electron. And this is the symbol for an electron. The E basically means electron. If you remember, the number in the upper left is telling you what the mass of this thing is, or what the weight of the thing is. And if you remember from much earlier in the course, we said that the electrons don't weigh enough to count. So basically, we are writing its mass as 0, and that's the common way that it's done. And the number in the lower left was supposed to tell you the number of protons or the number of positive charges. And if you remember, the electrons have the opposite electrical charge of a proton, and so you say that the electron has a charge of -1 here. So this whole thing that I'm circling here, the E stands for electron. We're talking, and because it's an electron, it has a weight of 0 and an electrical charge of -1. So, just to emphasize again, if you wait around long enough with a carbon-14 atom, it will one of the neutrons will turn into a proton and an electron. The electron gets fired off, and this is a completely different atom. And right now I'm not telling you what it is. You can pause and try to figure it out. Right now I'm talking about it as a question mark. And the way to figure this out is to basically count the number of protons. Well, how many protons does this have? 1, 2, 3, 4, 5, 6, 7. And if you remember, carbon only has 6 protons. So this thing is not a carbon atom anymore. If you wait around long enough with carbon-14, it will turn into something that is not carbon. If you look up which element has 7 protons in the periodic table, you'll see that this is now a nitrogen atom. It is now carbon-14, if you wait around long enough, turns into nitrogen-14. Because the mass is still the same, but the number of protons and number of neutrons is different. The number of protons is 7 now. So the question mark here is actually a nitrogen atom. And what you say when an isotope turns into a different material, when it turns into a different isotope, you say that the original isotope decayed. That's basically what happened to the atom. That's the formal term that you use for saying that one isotope turned into another. You say that the isotope decayed. This particular type of decay has a special name. It's called beta decay. This is the Greek letter for the word beta. And beta decay is when you have an isotope and one of its neutrons turns into a proton and an electron. And so it's not just carbon-14 that decays by beta decay. There are other isotopes that do it as well, but this is kind of the classic example. And just to emphasize again, beta decay is when you have some isotope, it doesn't have to be this one, but some isotope where one of the neutrons turns into a proton and an electron. The electron basically gets fired off into the distance, and your isotope turns into a completely different element. In the case of carbon-14, what happens is you start out with carbon-14, one of the neutrons turns into a proton and an electron, the electron gets fired off, and your carbon-14 turns into nitrogen-14. And the way that we would write that is we would write capital letter N. The mass is still the same, it still has a mass of 14 Daltons, but the number of protons, or the number of positive charges, is now 7. So this is called a chemical decay reaction, if you want to call it that. You basically have one isotope decaying into a different isotope, and it's also spitting out an electron. One thing that you might want to notice, and this is relatively important for this chapter, is that these types of decay reactions balance in a way that's similar to the type of balancing reactions that we discussed earlier. These types of balancing reactions are actually easier, in my opinion. What you have to realize is that the weight of everything that you start with on the left has to equal the weight of everything that you end up with on the right. So how much did everything weigh on the left? Well, we only had one thing, and it had a weight of 14 Daltons, or 14 atomic mass units. So everything on the right side of the equation has to weigh a total of 14 Daltons. The nitrogen here weighs 14 Daltons, and the electron weighs 0. So the weights match. We started with 14 Daltons, we ended with 14 Daltons worth of material. The other thing that has to match is the total number of positive charges. How many positive charges did we start with at the beginning? Well, this carbon had 6 positive charges from 6 protons. How many positive charges did we end up with at the end? Well, the nitrogen has 7 positive charges. The electron has the opposite charge, or a charge of -1, and 7 plus -1 is also equal to 6. So we started with 6 positive charges, we end with 6 positive charges. And that's how you can basically tell if your decay reaction is written correctly. So that's beta decay. I will show you a couple of examples on the next slide as well. On this slide, we are going to do another example of beta decay. So the question that I'm asking in this case is, what is the question mark in the following chemical reaction equation? So here's the equation. I am basically saying we have an isotope of cobalt. CO is the symbol for cobalt. This isotope has a mass of 60, so if you wanted to give it a name, you could call this cobalt 60. And apparently, if you wait around long enough, cobalt 60 will spit out an electron and it will turn into something else. What that means is that if you wait around long enough, cobalt 60 will undergo beta decay. It will decay into something else and spit out an electron, which is what beta decay is. And one thing to emphasize, just in case this letter is confusing, or this name, beta decay is one type of decay. There are other types of decays, and it was called beta decay because someone found a different type of decay before this, and they called it alpha decay. So this was the second type of isotope decay that was identified. So here we have cobalt 60. It will eventually spit out an electron and turn into something else. The question is, what something else does it turn into? Well, as I mentioned in the previous slide, this is kind of like balancing an equation. The weights of everything that we start with on the left have to equal the weights of everything that we end up with. Well, how much does everything weigh on the left? Everything on the left has a mass or a weight of 60 Daltons. That means everything on the right has to weigh 60 Daltons as well. And as you probably recall now, the electron over here weighs nothing. So whatever this question mark is, it has to weigh 60 Daltons. So we're already beginning to figure out what the question mark is. Whatever it is, it weighs 60 Daltons. Then we're going to need this strip of the periodic table as a reference. You can basically look up cobalt and figure out how many positive charges it has. Cobalt has an atomic number of 27. What that means is that all cobalt atoms have 27 positive charges. And the other thing that you need to balance, as I mentioned on the previous slide, is you need to balance the total number of positive charges on the left side and on the right side of the arrow. So if we started with 27 positive charges, we have to end with a total of 27 positive charges on the right side of the arrow. The electron has a charge of -1, so we have to figure out how many positive charges plus -1 will equal 27. And to figure that out, you can do some algebra, but basically the number 28 plus -1 will equal 27. What that means is this question mark has to have 27 positive charges, 28 positive charges, or 28 protons. And if you look up on the periodic table, the only element that has 28 protons is nickel. So we've now figured out the identity of this question mark. If you wait around long enough, cobalt-60 will decay into nickel-60 and it will spit out an electron. So the correct filled-in version of this beta decay equation is that cobalt-60 decays into nickel-60 plus an electron. So that is another example of beta decay. And obviously there are other isotopes that will also undergo beta decay. But the idea behind these types of problems is that if you're given a question mark in the reaction, you can figure out what the question mark is by making sure that the weights of everything on the left and right side of the arrow balance, and making sure that the number of positive charges on the left side matches the number of positive charges on the right side of the arrow as well. The other thing to point out as far as beta decay is concerned, before we finish up summarizing beta decay, is that whatever isotope you start with, it will always turn into the element to the right of your starting element. So if we start with cobalt and it undergoes beta decay, the cobalt will turn into nickel. If we started with nickel and it underwent beta decay, the nickel will turn into copper. And this is true always for beta decay, because with beta decay you are always gaining one proton, and if you gain one proton, you basically go up one in the periodic table. So that is sort of one of the characteristics of beta decay. Whatever isotope you start with, the ending isotope will be one to the right on the periodic table. And that's it for beta decay. We are going to do a couple of other types of decays on the next in the next couple of sections.